Morning, everybody. So we're going to finish up chapter 19 today, and then I'm going to get started in on chapter 20. I'm going to try to get us caught up just a little bit. And then on Friday, as I mentioned on the remind email, that we'll have an inverted lecture over 18 and 19 on Friday. So I'm not going to be in town on Friday, or in my office anyway, and so my graduate student will be in here helping you with your inverted lecture on Friday. So today we're going to really talk about two reactions. We're going to talk about Michael addition, or Michael chemistry, as some people call it, and we're going to talk about Robinson annulations. And so, again, a lot of the stuff that we're talking about now is not really new in a way, but Michael chemistry is just a bit different than things that we've talked about before. And so when we've talked about carbonyls in the past as electrophiles, we've talked about the carbonyl carbon itself functioning as the electrophile, right? So nucleophiles will attack the carbon of the carbonyl. For example, Grignards, whatever, amines will attack there, and the chemistry will occur. However, if you have an alpha-beta unsaturated carbonyl-containing compound, here I'm just going to use a ketone, we can draw additional resonance structures for these molecules that reveals that we actually have more than one electrophilic site in these alpha-beta unsaturated systems. So as we know, we can draw this resonance structure. And what bond are we breaking to draw that resonance structure?
Pi bond.
Which pi bond? The carbonyl oxygen pi bond, right? So the carbon of the carbonyl oxygen pi bond is being broken, and we end up with a positively charged carbon and negatively charged oxygen. Now that positive charge, is that it? We can resonance delocalize that because that's kind of allylic, right? And in fact, we can draw a resonance structure where we have a positive charge on this terminal carbon of the alpha-beta unsaturated ketone, okay, and put the carbon-carbon double bond here. And so, so if we had an alpha-beta unsaturated carbonyl system, and we were going to react this with a nucleophile, we have two potential sites that the nucleophile can attack. It can either attack the carbonyl carbon, and we've already seen that, or it can attack this terminal carbon of the alkene. So we can actually have a nucleophile attack here, this pi bond can move there, and then the electrons can move up, okay? We call this carbon of the alpha-beta unsaturated system the Michael carbon. Okay, after Michael who discovered this chemistry, all right? And so when we're talking about Michael addition chemistry, we're talking about the addition of nucleophiles at the alkene carbon of an alpha-beta unsaturated, at the beta carbon, okay, or the Michael carbon of the alpha-beta unsaturated carbonyl-containing compound, okay? And so we can have nucleophiles that will either add here, or we can have nucleophiles that add there. And the trick for you all in this chemistry is knowing what nucleophiles do what. Okay? There are nucleophiles that simply attack the carbonyl, and there are nucleophiles that prefer to attack the Michael carbon. Okay? And so if we have a nucleophile that adds at the carbonyl carbon, we just call this simple addition. Simple because you already know it. It's also known as 1,2 addition, okay, because you're adding across atoms 1 and 2. Okay? And so if a nucleophile attacks the carbon of the carbonyl, you simply get an alcohol, and this alcohol is on the allylic position, so you're making what are known as allylic alcohols. Okay, but nonetheless, it is a secondary alcohol in this case, depending. Well, if we assume that that's a hydrogen. Okay, could be a tertiary as well. Now we can also have the nucleophile attack at the Michael carbon. Okay, and we get what's called an enol intermediate from this reaction. Okay, are enol stable? They are not, and so they tautomerize and give you either the aldehyde or the ketone, depending on what this is. Okay, and so the trick again is going to be whether or not the nucleophile prefers to attack at the carbonyl carbon or at the Michael carbon. This other type of addition we call conjugate addition or 1,4 addition. And we've heard that term before, haven't we? Where else have we heard the term of 1,4 addition? In thermodynamic products, right? Which were the addition of what to what? I mean, what were the reagents? You're right. Pardon? Okay, so when we were adding some type of electrophile right across a conjugated pi system, like butadiene or something like that. We could have 1,2 addition, or we could have 1,4 addition, right? So we could add HX or X2 or whatever the case may be in a variety of ways. And so we're seeing the same kind of stuff here. So we can, again, have 1,2 addition and 1,4 addition. So again, nothing particularly brand new in terms of terminology for you, okay? So let's look at some experiments. So let's say Alex comes into the lab and he has this 3-pentene 2-one, which is an alpha-beta unsaturated ketone, right? And so we have this alpha-beta unsaturated ketone. He reacts this with methyl magnesium bromide, and he goes and works up the reaction afterwards, and what he finds is that 72% of his product is this alcohol, and only 20% of the product is where the Grignard has added at the Michael carbon and gives him this ketone, okay? So Grignards like to do what then? They like to attack carbonyls. You're going to find that Grignards and alkyl lithiums prefer simple addition. The major product of a Grignard reagent or an alkyl lithium will be the addition of the nucleophile to the carbonyl carbon. However, let's say John is taking this alpha-beta unsaturated ketone, this 4-methyl-2-cyclohexene 1-one, and he's reacting it with, what kind of reagent is this? We've seen these before. Those are organocuprates. Where did we see those before? Ketones from what? Pardon? Acid chloride. So an acid chloride plus an organocuprate gives us a ketone. Well, these organocuprates can also react with alpha-beta unsaturated carbonyl compounds, and when we do that chemistry, lo and behold, look what we see. We see absolutely no addition to the carbonyl. The only thing that we see are 2 diastereomers because this is a chiral center, and so you can have trans and cis addition, and don't worry too much about that. But in all cases, the nucleophile attacked the Michael carbon, okay? So what can we say about organocuprates? They don't do simple addition, right? They do conjugate addition or 1,4 addition or Michael addition, however you want to think about it, okay? They like to do that type of addition, okay? Cyanide prefers to do conjugate addition. So cyanide's a pretty good nucleophile. It attacks the Michael carbon. You go through the enolate intermediate, which then gets worked up with a little bit of acid, and you form a new carbon-carbon bond at the Michael carbon. 95% yield. Cyanide prefers to do 1,4 addition, not 1,2 addition when given the choice, okay? Amines make good nucleophiles, okay? But they also prefer to do Michael addition and not simple addition. So if I took this primary amine and I took a ketone that wasn't alpha-beta unsaturated, what would the product be that I get? If it wasn't, it was just a regular ketone. A ketone plus a primary amine gives me an imine. Yeah, you were close, right? So an imine. A secondary amine in a ketone gives me a enamine. A primary amine or a secondary amine plus an alpha-beta unsaturated ketone gives me a new amine. It just adds at the Michael carbon. It leaves the ketone alone, okay? Enolates. We know that enolates are good nucleophiles. Enolates also react at the Michael carbon and give new carbon-carbon bonds to give these carbon-carbon bonds, again, not at the alpha carbon, but the beta carbon of the original alpha-beta unsaturated ketone. So enolates also prefer to do Michael chemistry when given the option. Okay? We talked about, last time, we talked about aldol, and we talked about Claisen and Diekmann, right? And those we were generating enolates and enols that would react with carbonyls. Okay, but here the enolates are going to react with the at the Michael carbon. Okay, So, before we get to talking about the Robinson annulation, let's do a little bit of stuff on the board here. So from what you just saw, how would you memorize for the test how to know which nucleophile is going to do what? The way that I think about this is that I say that Grignards and alkyl lithium reagents do 1,2 addition. Everything else is 1,4. That's real easy for you to remember. Grignards and alkyl lithiums will do 1,2 addition as the main product. Okay? But everything else will prefer to do 1,4. Okay? So let's look at an example where, I don't know, let me just make this up. We've got an alpha beta unsaturated ketone, and Jack's going to react this with sodium cyanide. I don't know, say DMSO as solvent. And then he's going to throw in iodomethane after that reaction is completed. What's the product going to be? Well, we don't have meta here, right? Because this isn't an aromatic ring. So I see what you're saying. Okay. What's going to happen in the first step? Okay, or the metacarbon, like he was thinking about, right? And what kind of addition is that? It is 1,4. It's also known as Michael addition, right? And so we're in DMSO. We have no acid around or anything. So what am I actually going to get? That cyanide's going to add there. That's true. Pardon? I'm going to get a negative on the oxygen, right? And so what is that? Pardon? That's an enolate, right? So Jack gets an enolate from the first step. We can do something with that enolate, right? So it's a sodium enolate. We don't really need to worry about that. Let's just keep everything nice and balanced. And now at the end of that reaction, he dumps in iodomethane. Now what happens? SN2. What's going to be the nucleophile? What part of the enolate? I've got two nucleophilic regions of an enolate. It's either the oxygen or the carbon. Think it's going to be the oxygen? It's going to be the carbon. Remember, the carbon most of the time behaves as the nucleophile in enolate chemistry. And so we're going to have this reaction occurring. And how many products is Jack going to get? He is going to end up with 2 products. So there's some stereochemistry we have to take into account, right? So what's the possibilities? I haven't shown any stereochemistry, right? What are the possibilities? Okay, so let's just make it forward. Okay. Plus we'll get what? And how are those with respect to one another? Those are enantiomers. So that's really one product that he'd be able to notice by anything. Is there another possibility? Okay, so he could have the situation where that, and so he would also end up then with the enantiomer of that, since we're going down that road. Okay, so really 4 possible products because there's 2 chiral centers, but 2 of those are diastereomers, right? So these relative to these are diastereomers to one another, right? So you'd get a pair of diastereomers that you'd be able to distinguish in NMR, but you'd really have 4 different products in that case, okay? This is one of the powerful things about Michael chemistry. You're doing an addition at that Michael carbon, but you're getting an enolate intermediate that you can then exploit and do something else with. You could simply dump it into water and protonate it, and it's an enol that then tautomerizes to the ketone and puts a proton on that alpha carbon. Or you can dump in some other electrophile to react with that enolate and actually form more complex structures. So the cool thing about the reaction that we just talked about was we just made 2 carbon-carbon bonds in a single, well, 2 reactions, but in one pot. So if Anna came in and ran that reaction, she would add the sodium cyanide and the ketone together in the solvent, let that reaction go, and then she would just simply add the iodomethane after that reaction was over into that same reaction flask. All right, the Robinson annulation is the reaction between an enolate and an alpha-beta unsaturated carbonyl-containing compound to actually form a variety of rings. Nothing new here, but we're starting to mix reactions together. The Robinson annulation is nothing more than a Michael addition followed by an aldol reaction. Okay, so Sir Robinson figured out that he could take 2 other people's reactions and get a Nobel Prize, all right, which was kind of cool, all right? Now, what's important about this, and the reason it was meritorious of a Nobel Prize, was if you look at the product, what's special about it? Multiple rings fused together, very important in natural products like steroids. So making steroids, kind of important here. We've got some pi bonds, we've got some carbonyls. We're really starting to get to the point now where we're talking about synthesis of functionally grouped complex structures. Okay? Just about every chapter that we've been in previously, we've talked about making one functional group at a time, or one carbon-carbon bond at a time. But what we're doing now is we're making multiple carbon-carbon bonds and multiple functional groups all in a single reaction, and we're building up what we call molecular complexity, okay? And if you ever take one of these courses at the graduate level, that's exactly what you're going to be focusing on, is how you build molecular complexity, okay? But we're going to keep it pretty simple. We're going to keep it to fairly small ring systems. So if we look at this, if we take this 2-methyl-1,3-cyclohexadienone, we know that these hydrogens are going to be fairly acidic, right? Or this hydrogen, there's only one, excuse me, right? Why is this hydrogen more acidic than, say, the hydrogens on this alpha carbon or this alpha carbon? Okay, it's alpha to 2 carbonyls, right? And so if we remove this hydrogen, the resonance structures are actually, we can draw quite a few resonance structures, and that means it's going to be more stable, right? So yes, I've got acidic hydrogens here, I've got acidic hydrogens here, but this is going to be the most acidic hydrogen, and so we can get away with reacting this with a fairly weak base, sodium hydroxide or potassium hydroxide, right? So if I can get away with using a hydroxide base, what's going to be the pKa range for this hydrogen approximately? Getting close. 11, 12, 13, yeah, somewhere in that ballpark. It's going to be below 16 because we know that hydroxide has a pK of 16, right? So we're going to generate the enolate. That enolate is then going to attack the microcarbon, and we're going to form a new carbon-carbon bond right here. But things aren't over. This reaction just does not stop here, okay? So we've got these 3 alpha hydrogens here. They've shown them in blue. Hydroxide will generate a little bit of enolate here. Notice that they've drawn this as an equilibrium. How much of the enolate can we expect to generate from a ketone with hydroxide? Not much. Give me a ballpark though. I mean, that's right. 10% would be okay if we were using something like tert butoxide. But here we're using hydroxide, so about 1% or less, right? And so you generate a little bit of this enolate, not a lot, but now we've got an enolate and we've got a carbonyl. This enolate attacks the carbonyl. What's the name of that reaction? That's the aldol reaction. Again, a reaction you already know. So that enolate attacks, you end up now with an alkoxide. This alkoxide abstracts a proton from the methanol as a solvent, makes an alcohol, and then this dehydrates very, very rapidly under these conditions. It loses water. And why does it lose water so readily? That must mean that this is more stable than this, right? Why is it? Excuse me? Yeah, so we have a resonance stabilized conjugated system, right? Here we do not. We just have the isolated pi bonds and the carbonyls, no real conjugation. And so this is going to be less stable than this, and so this will lose water very, very, very readily to give you this alpha-beta unsaturated system. And so actually, we could actually now use this to do Michael addition here if we wanted to. We could do simple addition to this ketone or simple addition to this ketone. We can start to do other reactions with these types of materials. And you might think, well, 65%, you know, if you got a 65% on anything, that's a D in class, right? But this is pretty good for this reaction, right? Because we're just taking these two things, mixing them together with a little sodium hydroxide and methanol and letting it stir. All of this is happening as the reaction occurs. Okay, these are not two distinct steps. So you all need to know that the Robinson annulation is what? It's the mixture of two reactions, and what are they? Michael and aldol. Is it aldol and Michael or Michael and aldol? Michael and aldol. Order matters. It's going to be the Michael first, followed by the aldol reaction. Okay? The actual process, that's right. Yeah, Michael and aldol, process-wise, is not the same as aldol and Michael. Okay? Now, why is it that it's this enolate that forms and not an enolate, let's say, from this alpha carbon? Couldn't I generate an enolate from that other alpha carbon? That is true. So what are we talking about? Talking about steric hindrance, which is also talking about thermodynamic and kinetic, right? So the kinetic enolate always forms first, correct? And so this one would give us a kinetic enolate because there's 3 hydrogens here. And the pKa of these hydrogens is going to be more or less similar to the other alpha hydrogens. But this forms first. Okay? Now, this is an equilibrium though, right? So why is it still that this one is the one that adds and not one of these others?
Because it allows for a sigma bond.
Okay, go. Correct, but take that just a little bit further. We're forming a 6-membered ring. So when this attacks, we get a 6-membered ring, which is actually thermodynamically stable. It's a pretty stable ring to make. If we had made the enolate here and that attacked, what kind of ring would we get? 1, 2, 3, 4. Would that be a stable ring? It is not. So even though we can generate an enolate here, it's going to be reversible. It's not going to form a stable ring. It's this enolate that does all the chemistry that we're interested in. Okay? All right. Fill in the boxes for me, please. Work with your partners. Shelby, you can work with whoever you want to. Don't Don't look up the answer.
Because I say it was on the slides. I scrolled down, I was like, oh, empty boxes, man. I didn't see it, so did not see it. Okay, I might have some papers. Prepare.
All right. So what's going to happen in this first reaction? I'm going to add the methyl of the Grignard to what? Carbonyl carbon, right? So in any time you see these types of problems, identify the nucleophile and figure out what kind of chemistry it likes to do. So I know that a Grignard likes to do 1,2 addition or simple addition or just addition to the carbonyl, however you have this stored in your head. That's fine. And what's my product going to be? What functional group am I going to get in the product? An alcohol, right? Oh, heck, they all showed up. All right. So yeah, you're going to end up with an alcohol. The second case, right, we've got a cuprate, and so it's one of these methyl groups is going to transfer to here, and we're going to end up forming a new carbon-carbon bond on the alpha-beta carbon, right? So beta right there. And then what's the name of this reaction? Robinson annulation. And so it's going to be a what followed by what? Michael followed by an aldol. And so the nucleophile for the Michael addition is what? Pardon? The enolate. The enolate from the diketone that we have there, right? So we're going to do that addition followed by what reaction? Aldol, right? Good. And we're going to form 2 fused 6-membered rings with a pi bond. How else have we learned to make 6-membered rings? Diels-Alder and what was the name of the reaction last time? Dieckmann. Yeah, so Dieckmann cyclization, right? So last time we learned about the Claisen, we learned about the Dieckmann, we learned about the aldol. Today we learned about the Michael, and we learned about the Robinson annulation. A lot of names, right? You're going to have to figure out how to keep those straight in your head. Okay? But the chemistry is not all that new. Okay? A Claisen deals with what? What functional groups are we dealing with in a Claisen reaction? What starting materials do I need for a Claisen? Huh? I do need an enolate, but of what?
Ester.
Of an ester. So two esters react to form what's the final product? Beta ketoesters. Diekmann. It's a beta ketoester, but it's part of a six-membered ring. It's a way to form a six-membered ring. Michael chemistry does what? 1,4 addition and makes nucleophile carbon bonds at the beta carbon of an alpha-beta unsaturated carbonyl. Okay? And then Robinson annulation forms these fused six-membered rings, these two fused six-membered rings, by using a Michael followed by an aldol. Okay? All right, so let's look at some problems that you might find on an ACS standardized exam. Which nucleophilic reagent, Z, as they call it, will give the most 1,4 addition product with methyl vinyl ketone? B is the correct answer. Let's go through the others, though. Lithium aluminum hydride will do what? It will reduce the carbonyl to an alcohol, right? C, methyl magnesium bromide will do what? 1,2, and add to the carbon of the carbonyl and form an alcohol. What is D? That is a Wittig reagent. What does a Wittig reagent do? Where? At the carbonyl. So it replaces the carbon-oxygen double bond with a carbon-carbon double bond, right? So all of these reagents would do chemistry on this molecule, but not the same chemistry, okay? So these things are starting to rattle off. I'm happy to hear that, okay? This stuff should start rattling off, okay? That's good. Question 17, which reagent will accomplish this conversion? Did I hear B or D? What? D. It is D. It is the cuprate. When I look at this problem, what I notice is that I'm doing Michael chemistry. I'm adding something to the Michael position or the beta position, right? And so when I look at all those reagents, D is the only one that can do that. What would A do? Would it do SN2? How would it do SN2? It is useful as a reagent in SN2 chemistry, but can it do SN2 here? Actually, it's a little bit of a trick question. I mix those two things together, not a thing happens. No reaction. B, what would happen? It would do 1,2 chemistry. You'd end up with an alcohol. What would C do? It would also do 1,2. Grignards and lithium reagents do 1,2 addition, right? All right. Let's get into chapter 20 a little bit. We'll go ahead and get started on that. All right. Chapter 20, we're starting to talk about amines. Again, not a whole lot new because we've talked about amines at just about every turn this entire sequence of the course, right? How many types of amines can we have? We can have 3. We can have primary, secondary, and tertiary. What if I have a quaternary? It's a salt, right? Amines must have a lone pair of electrons. So we're not going to talk a whole lot about nomenclature today. We'll talk a little bit. We'll talk about some interesting amines and then maybe some spectroscopic properties. I don't know that we'll get to the preparation of amines. We've only got about 15 minutes left. But we'll get started. Okay? So you all have already identified the fact that we can have primary, secondary, and tertiary amines. They are amines by virtue of the fact that the nitrogen has a lone pair of electrons. And we know that amines can behave as nucleophiles. We know that they can behave as bases, right? So we know all that kind of stuff. We know that a primary amine plus a ketone gives me a imine. We know that a secondary amine and a ketone gives me an enamine, right? We know all that kind of stuff. We know that we can utilize amines for a variety of purposes. So they can behave as bases, they can behave as nucleophiles, and they're all they're pretty important things. Okay. We know that they can react as a base. If we take the amine and react it with an acid, we end up with a quaternary ammonium salt, where one of the bonds is to hydrogen, at least one of the bonds is to hydrogen. We can also react it as a nucleophile if we have some type of electrophile. Let's say it's carbon. We can form a new nitrogen carbon bond. We call those quaternary ammonium salts. You all have already demonstrated you know that pretty well. And the take-home message of this is that all the chemistry of amines is really dominated by that lone pair, right? Really, and it just depends on what they're reacting with. If they're reacting with a Bronsted Lowry acid, right, they're just going to function as bases. If they are going to react with some type of Lewis acid like iodomethane or something like that, then they're going to behave as a nucleophile. Okay? So, given that information, how could you make that molecule? I don't have it in the lab, but I have everything you need to make it. You need to make that salt. How could I make it? Throw some acid on there. I need to know what that means. H2SO4? What I'm asking is how do you make that salt? Just taking sulfuric acid and throwing it in the flask isn't going to do it, right? I'm going to need something. What might I need to make this molecule? It's just tosylate. How can I make that? Bit grasping for straws there.
Are we making them at the same time?
What do you mean? You're making the salt. That is a compound. That is a salt compound.
Could you take a tertiary amine and put it with like a phenyl tosylate?
Okay. Yeah. So we can think about, if we think backwards, right? If we had this amine, which is trimethylamine, plus we had this tosylate, it's simply just an SN2 reaction to give the product. Okay? Is that the only way to make this? That's probably the most efficient way, actually. But what's another way to make it? Do I have to have this tosylate? Actually, I could have methyl tosylate and look at one of these bonds, right? Either way would work just fine, depending on what starting materials you have. This way is the most practical, because trimethylamine you can actually buy quite easily. It's a gas at room temperature, and it smells like rotten fish. You know when the chemistry is going on this floor because it literally smells like a bad sushi shop. Trialkylamines are actually part of the decomposition products of fish as they rot. And so if you've ever heard, it smells like fish, you should never eat sushi that smells like fish, because when fish starts to smell like fish, it's actually starting to rot. Fish that's healthy and fresh and it doesn't smell like fish, it has no smell at all. So if you start to smell that fishy smell, not good sushi. We know that the structure of the amine, when we look at the nitrogen, we have an sp3 hybridized nitrogen atom. We have a lone pair of electrons. The bond angles are about 108, so it's close to tetrahedral if you count the lone pair of electrons, but we typically call this pyramidal. Notice the bond angle is a little more compressed than what we would expect for a tetrahedral atom. Tetrahedral atoms have bond angles of what approximately? 109.5-ish, right? And this is at 108. Why is this bond angle a little more crowded? No, not the charge, but But electrons, yeah, so it's electron and repulsion. So electron pairs repel, but electron pairs also repel bonds, right? And so you have that going on here. So it's part of the Vesper theory. We know that an amine with 4 different groups attached to it, in theory, can be chiral. So the lone pair of electrons is a group, R prime, and H. Those are all 4 groups. Around that atom, I can have a non-superimposable mirror image. However, these amines you really can't make as one enantiomer. Okay? Does anybody remember? We talked a little bit about that when we were talking about chirality in chapter, what was that, 5 or 6? And what you might remember is that amines undergo inversion very, very easily. Okay, so we called this umbrella inversion or umbrella flipping. And so if you had this enantiomer, it will readily go from an sp3 hybridized atom to an sp2 hybridized atom and then flip to the other, and this happens back and forth. So you can spend a lot of time trying to make one of these enantiomers, but it will just undergo this so-called umbrella inversion, and you get this interconversion of one enantiomer to the other. So the only way to have a nitrogen atom that is truly chiral that you can isolate and do something with is if you have 4 bonds to nitrogen. That would be an ammonium salt. Once you have the lone pair of electrons, the barrier to inversion for these systems is actually quite low, and they will interconvert quite quickly. Okay? So here, again, because we have no lone pairs of electrons, you can actually isolate quaternary ammonium salts as either R or S, but not the free base amine. Nomenclature, real quick. You all can spend most of your time figuring this out. It's pretty straightforward. You can either name these using the systematic or common naming systems. To assign the systematic name, you're going to find that longest continuous chain. You're going to change the E of the alkene with the suffix amine. So hexyl amine would be 6 carbons, right? Normal way to do it. Most people use common names for very small ones, right? So, for example, CH3NH2, the systematic name would be methanamine. I even have trouble saying methanamine, but the common name is methylamine, and that's how most people think of this molecule, is methylamine. This molecule, methylamine, is the famous amine. If you ever watched the Breaking Bad series, this is the one that they robbed the train for. It is a very vital, important component of making methamphetamine. It is also regulated because of that. Okay, so I can get methylamine in my laboratory pretty easily, but we have the ability to do that. You can't just go down to the local drugstore and buy methylamine, okay, because it is so useful for making illicit drugs, okay. The systematic name for the one you see there with the cyclohexane ring would be cyclohexanamine. Again, that sounds kind of weird to me, but I always think of it as cyclohexylamine. Okay, so most of the time we're going to go with this common naming system as opposed to the systematic, but both are correct. Okay, there are a few aromatic amines that we've already talked a little bit about. The anilines. Anilines are very, very important class of compounds. Aniline, of course, is an aromatic ring, a benzene ring to be specific, with an amine group attached to it, NH2. We can also have this thing here. This is also an aniline derivative, but it's called N-ethyl aniline. What does that name tell us? What does the N mean? That's right, because if I said ethyl aniline, you don't know if the ethyl group is on the nitrogen or if the ethyl group is on the aromatic ring. But the N, the capital N that is italicized, tells me that the alkyl group is going to be attached to the nitrogen of the aniline, not the aromatic ring. Okay. We've also learned about these other types of nitrogen-containing materials here before: pyridine, pyrrole, papyridine, and pyrrolidine. Very useful molecules as bases. Okay. We also know that the physical properties in terms of boiling points and solubilities for these things follow this general trend. So primary and secondary amines will typically have higher boiling points. than other similar compounds. So if you look at the situation here where we have this ether, which can't form hydrogen bonds, molecular weight is 74, which is very similar to the amine. You can see that it has a boiling point of 38. The amine has a boiling point of 78. It's because of hydrogen bonding. But why is the alcohol so much higher in boiling point than is the amine? Stronger hydrogen bonds. That's right, because oxygen is more electronegative than nitrogen. It forms a stronger hydrogen bond. And so you expect alcohols to have higher boiling points than amines. Okay? Solubility follows the 5-carbon rule. Typically, you'll find that amines are soluble in organic solvents regardless of their size. And we can also use acid-base chemistry to extract amines from complex mixtures, right? So you can get amines to dissolve in water by making salts out of them, by reacting them with HCl and other things. Infrared spectra. Typically, what you're looking for in the amines is for stretches here in the hydrogen region, okay, somewhere just under 3,500. If you have a primary amine, you're going to see what we call the amine doublet. You're going to see 2 stretches. Why do I see 2 stretches for a primary amine? Yeah, I have 2 hydrogens, right? But why does that give me 2 stretches? Why do I see 2 signals for 2 hydrogens? Is it a requirement that I see 2 for anything that has 2 hydrogens? No, sometimes you just see 1 peak, right? Why is it that these 2 hydrogens can give me this, what we call the doublet? Because there are 2 ways that these can stretch. I can stretch both hydrogens at the same time, and that gives 1 peak, or I can do what? So I can have what's called an asymmetric stretch, where 1 hydrogen is coming in while 1 hydrogen is going out, or I can have both hydrogens going out and in at the same time. Those are 2 different frequencies. So you will see a doublet. A secondary amine, however, only has 1 hydrogen. You're only going to see 1 peak. It can only do this. Pretty boring. And then for the tertiary amine, you will have an absence of an NH hydrogen. So you can identify primary, secondary, and tertiary amines by looking at the number of stretches that you have. All right, we will pick up with this on Monday.